Hi everyone. We're going to learn about a technique for actually solving differential equations that's called separation of variables. It's a really nice one. It doesn't work on everything. Not all equations are separable, but when it works, it's pretty simple and easy to understand. And I think the messiest part, oh, sorry, my dog found a squeaky, is the solving at the end, the algebra. So the idea would be that if we have a differential equation that we can write as a product of a function of x, no, stop, and a function of y, then we can manipulate that equation in a way that allows us to separate variables so that y's are on one side with dy and x's are on one side with dx, and there's no mixing. So the first part of this is pretty easy. So you can see here I just moved my f of y to the other side with dy dx. And just for the sake of not having to write fractions over and over, 1 over f of y is still some function of y, so I'm just going to rename it h of y. So now I have h of y dy dx is equal to g of x. And just as we've done with substitution and parts and trig sub, we can manipulate that a little bit more and move the dx up so that we have h of y dy and g of x dx. And then the idea is if those two things are really equal, then we should get the same thing when we integrate both sides, give or take constants, right? But we'll include that when we're solving. So if you can separate your variables, you can just use integration and solve for your function. So that's separation of variables. Enough. So let's run through an example. This one's actually from your slope field homework, so I recommend going back and looking at your slope field after you've watched this one and just looking at solution curves. I don't have an electronic copy of that, or I would paste it in here. So dy dx equals xy squared. Okay, so for starters, and you can choose your order, I'm going to go ahead and just move the dx up as my first step. So I can see that the x is with the dx. I would like to get rid of the y squared, and I can do that by dividing both sides by y squared. So it's really important. Adding or subtracting won't do the trick. This has to be something where you can divide out all the y's. Or multiply, that would work as well. Okay, and it's officially separated. Once you get it separated, you can integrate. And the deal is the reason you have to separate is because you cannot integrate y's with respect to x or x's with respect to y without getting a lot more into what that actually does. So not doing it here. You can do multivariable, you'll do more stuff like that. Okay, so first I need the antiderivative of y squared with respect to y. And since it's with respect to y, that's just my variable. The power would go up to -1, and I'd have to divide by -1. So that's what I get on one side. I will need a plus c, but I don't need one on both sides. I just need one. On the other side, the antiderivative of x is x squared over 2, and there's my plus c. So I'm not done. I want to solve for the function if at all possible, and it should be possible in all the ones you're working with. And that is just algebra, but there's some weird stuff that happens with the constant. So remember that plus c is an arbitrary constant. It's basically representing any real number. All real numbers could be c. So as we go, if we do something to the constant c, it might not actually really change the fact that it's an arbitrary constant. So I'm going to start by multiplying by y. And then I'm going to go ahead and just divide out all of that stuff. So I get y equals, I'm going to flip-flop sides on you, -1 over x squared over 2 plus c. I'm going to go ahead and multiply by 2 so that I don't have to look at the fractions and fractions. So I get -2 over x squared plus 2c. And this is one of those places. If c can be any real number and then you double it, you've still got any real number as your possible c value. So you don't really have to change it. If you want to call it a different variable name, that's fine. But here it's identical. Arbitrary, any real number, arbitrary, any real number. Okay, so I'm done with finding the general solution to the differential equation, and notice that the plus c is not a vertical shift here. It's not even really a horizontal shift. I don't quite know what that is. I'd have to play around with it and see. So they don't have to just be vertical shift anymore when we're solving differential equations. I'm not quite done because I was actually given a specific condition, so I'm looking for a specific solution. So I'm going to go ahead and plug in -1, 1. And I'm going to solve for c, so I'll start by multiplying both sides by 1 plus c. And then I'm going to add 1 to both sides. And then I'm going to divide by -1, and there's my value of my constant. So when I'm all done, I'll get y equals -2 over x squared plus 1. And that is the solution to my differential equation. So like I said, if you still have your answers to those in-class slope fields handy, go back and look at that one and think about what the solution curves look like and see if you can see that -2 over x plus 1 shape when you start at 1, -1. Okay, thanks for watching.